The best part about recording, mixing, mastering, and producing is that there's always more to learn. If you've been studying audio engineering for a while, you may think that there isn't anything new to dive into, but there's always something interesting if you do some digging. That said, let's cover 3 advanced audio concepts you've never heard of. Starting off, let's talk about bit shifting. So bit shifting is pretty rare in audio processors. It's a method for altering the placement of bits to increase or decrease the gain. Typically, when we alter the gain of a track within a plugin or with a fader, or when we adjust the amplitude of the left or the right channels using panning, we change the word length. By changing the word length, our computers can output the signal at nearly endless divisions or multiplications of the original audio. For example, say I reduce the gain by something really specific like 1.7 dB. Since each bit represents 6 dB of information, the word length needs to extend to represent a change smaller than 6 dB. This is convenient for sure, and it gives users more freedom to fine-tune a signal's amplitude, but there are some potential drawbacks. Now, some argue that these divisions cause increased quantization distortion, since the amplitude of the wave is set to something so specific that the bit depth can't adequately represent the change. For example, 16-bit mixing can handle a word length with 5 decimal points, meaning if we alter the gain to a specific level that requires a word length of more than 5 places, which is possible and pretty common, we'll get a rounding error. But with DAWs using 32 or 64-bit processing, which allows for much higher word lengths and subsequently greater precision, any rounding errors will be pretty minimal and likely inaudible. Now, with all of that in mind, bit shifting is an alternative to changing the word length when making amplitude changes. By shifting the entire bit series to the right, the amplitude is divided by 2, causing a 6 dB decrease in amplitude. By shifting the entire bit series to the left, the amplitude is multiplied by 2, causing a 6 dB increase in amplitude. The word length doesn't change, there's no potential for rounding errors. However, all changes are made in 6 dB increments. The same could be done for panning. Instead of changing the word length to reduce the amplitude of the right channel to pan the signal to the left, or vice versa, bit shifting could be used. Again, the idea is that it's closer to the original recorded signal. By retaining the original word length and sequence, it's just shifted in either direction, and with 6 dB of change being the smallest amplitude change that's possible. I'm not advocating using it over what your DAW uses to alter the amplitude, but if you're curious about it, some Air Windows plugins use this method for changing the amplitude and placement. They're free, so it's worth giving it a try. Let's take a listen to a rough mix, adjusted and panned using the DAW's pan pots and faders, then that same mix adjusted and panned using bit shifting. Let me know if you can hear a difference.
She reminds me of a cold, dark summer's night when I'm staring at the lights and I'm hoping that there could be something more here. She reminds me of a cold, dark summer's night when I'm staring at the lights and I'm hoping that there could be something more here.
Next up, let's cover temporal or time-based masking. So usually when I discuss masking, I talk about simultaneous masking. That's when either a loud sound or specific frequency covers up or masks another occurring at the same time. For example, if the vocal is difficult to hear, odds are roughly 250 Hz is too loud and it's occurring while the vocalist is performing. 250 Hz masks 3 to 5 kHz, making the vocal's consonants difficult to hear when they're both present. Temporal masking is masking to signals that occur at different times. For example, say I have a loud single sample click sound. Right before and after the click is a softly plucked note on a guitar. The area of the note right before the click and right after will be masked. When masking occurs before or preceding the loud sound, in this case the loud click, that's called pre-masking. When it occurs after, it's called post-masking. Now, interestingly, this masking occurs exponentially, meaning the degree to which the other signal is masked depends on its proximity to the masking sound. Roughly 20 milliseconds before the loud click and 100 milliseconds after the loud click will be masked, with the sound closest to the click incurring the masking to the greatest extent. Now, this is why, at least in my opinion, the ring of a snare is one of the most difficult things to get right in a mix. Not only is it a softer sound that's competing with other louder signals that are occurring simultaneously, but it's also occurring right after a loud signal that can mask it for up to 100 milliseconds. A possible remedy for this is upward processing, or maximization, that causes subtle wave shaping to lower amplitude aspects of the signal. By bringing up quieter details of the snare, we increase their amplitude relative to the peak, in turn reducing the effect of both temporal and simultaneous masking. To understand this better, let's take a listen to the first example that I gave, which is a loud click and soft note. I'll loop a soft piano note and then introduce a loud click. Although it's subtle, notice how the area around the click gets covered up. Get professional analog mastering that accurately translates what you hear in your head. Seriously though, when people work with us, they get results. That's why major industry professionals like Keith Urban's producer Aaron Schurz works with us, Grammy Award-winning AJ Castillo, Billboard #1 charted artist Megan Lindsay, Grammy Award-winning artist Toulis, The Voice singer Cody Ballou, Grammy-nominated producer Tyler Kane, Warner Music artist Ricky Young, and the list goes on. Watch the rest of this video, and at the end, use the link in the description to get direct access to us for personalized analog mastering that accurately translates what you hear in your head. Last up, let's talk about audio distortion occurring in nature. So when we think about distortion, we usually think about an amplifier that's adding harmonics, or maybe a DAW that's causing some clipping if the signal goes above 0 dB at the output. But sounds can distort naturally due to extreme pressure put on air molecules or the natural mechanisms in our ear. For example, we become somewhat familiar with the sound of a rocket taking off during a space launch. The quintessential crackling sound seems to just be part of the experience, but it's an interesting example of how air molecules can depart from their typical behavior. Usually, air molecules compress and expand gradually, resulting in sinusoidal waves or sine waves, or the gradual curved peaks and troughs that we're used to seeing represented in DAWs or oscilloscopes. But if the compression and rarefaction are intense enough, if the air molecules are displaced fast enough and the air temperature changes rapidly, air molecules no longer create a sine wave. They begin to create waveforms more indicative of saw waves, triangle, and square waves. Running audio from a rocket launch through an oscilloscope shows how distorted the sound becomes. And this isn't from the microphone or preamps clipping, this is the actual sound of the rocket without significant added distortion during the recording. Tying this back to mixing and mastering, this offers a really good reason to monitor at reasonable levels. Granted, you'll never mix this loud if you still want to hear, but it shows how significant air pressure begins to reshape waveforms, and it could give you an inaccurate representation of your mix, even if it's much subtler than this. The next way sound can distort naturally is through our auditory reflex. When we hear a loud sound, usually a rapid loud sound, our ears compress the incoming signal. The ossicles of the middle ear contract and reduce sound pressure, going to the auditory nerve, resulting in an effect very similar to optical compression with some adjusted parameters. Depending on the sound pressure level, it could take about 20 to 100 milliseconds before the maximum amount of attenuation occurs. After a couple of seconds, the attenuation is about 50% of the original level before it gradually goes back to normal, but various measurements show different results. Compression causes mild wave shaping, resulting in harmonic distortion. So just like the rocket launch example, if the waveform is being shaped from a sine wave to a different waveform, the result is distortion. So let's take a listen to compression designed to mimic how our ears react to loud sounds when other noises are present. The distortion is very subtle, but it's there nonetheless. Get professional analog mastering that accurately translates what you hear in your head. Seriously though, when people work with us, they get results. That's why major industry professionals like Keith Urban's producer Aaron Schurz works with us, Grammy Award-winning AJ Castillo, Billboard #1 charted artist Megan Lindsay, Grammy Award-winning artist Toulis, The Voice singer Cody Ballou, Grammy-nominated producer Tyler Kane, Warner Music artist Ricky Young, and the list goes on. Why waste your time creating masters that don't accurately translate what you hear in your head when you could instantly fix a problem by clicking the link in the description and working directly with professionals who have already done what you're trying to do? We've mastered thousands of songs that accurately translate what each client hears in their head, and it'll work for you too. Click the link in the description now and get direct access to us for personalized analog mastering that accurately translates what you hear in your head.